Hello everyone, so today we are going to solve two problems from Irodov as usual. I've already written down the problem, so I'm going to read it out and explain it to you simultaneously. So in this problem I have a chain of mass m which is forming a circle of radius r, and it is capable of slipping on the smooth round cone with a half angle theta. Find the tension of the chain if it rotates with a constant angular velocity omega about the vertical axis coinciding with the symmetry axis of the cone. Okay, so I've read the question. Let me draw the diagram and explain it to you what exactly it says. Okay, so let me draw the cone first. So hold on. So this is the slant surface of the cone. This is the other slant surface of the cone. Okay, and my ring is actually wound over this cone. Okay, so this is my ring which is actually wound over this cone. So this is the back side. This part is the back side of the chain. Okay, and this is the front side. Okay, um, it has been mentioned in the question that the mass of the chain is m. The radius that this chain at this position which it makes is equal to r. So this radius has been given to me as r, and the third thing that has been given to me is that it is rotating with an angular velocity of omega. The half angle of the cone has been given to me as theta. Okay, so given this information I need to find out the tension in the chain. Okay, let's observe what exactly is happening in this problem and try and solve it. So if I look at one small segment of the chain which is in contact with the surface of the cone, which is something like this, on this small segment, let's say that its mass is dm. Okay, the force that the surface of the cone is going to apply is obviously going to be in the normal direction. Okay, and its value is going to be equal to dn. This is a small normal force applied by the surface of the cone on the small segment of the chain with mass dm. Okay, now this dn has got two components. One is in the horizontal direction and the other one is in the vertical direction. The vertical direction of the vertical component of this dn is actually balancing the weight of this small segment with mass dm. Okay, so given that information I can write down a few equation. Okay, write down one equation actually. This half angle has been given to me as theta, right? So if I draw the FBD for this mass dm, there is one force dn acting in the vertically upward direction. Okay, not vertically upward direction, perpendicular to the surface of the cone. There is going to be weight acting in the downward direction, and obviously there would be some tension on this segment, which I'm not mentioning right now. If I look at it from the horizontal plane, it will start making sense. Now I need to write down, right now I need to write down an equation along the vertical direction. So if this angle is theta, this angle is also going to be equal to, this is going to be theta, right? This angle is going to be 90 degree minus theta, sorry, my bad. So this angle is nothing else but 90 degree minus theta, So the vertical component of dn is going to be dn times sine of theta. This balances the weight of the small segment of mass dm. The weight is nothing else but dm times g. Okay. Now with this information, I can write down dn as dm times g by sine theta. Also, I can write down one more thing. If I look at the ring from the top, okay, it would look something like this, right? This is going to be the ring, and it is going to be rotating with an angular velocity of omega. Radius would be r, and I'm just looking at a small segment. Okay, I was looking at this segment, right? This, let's say, located somewhere here. Okay, its mass is dm. Alright, so this is the top view of the chain. Okay, alright. If I look at this small segment dm from the top, if I zoom this segment out, it will obviously make an arc. It will make a very small arc, right? Something like this. It will make an arc. There would be tension, okay, on the ring, okay, on the chain actually. And let's say this small arc subtends an angle equal to d phi, okay, on the center. Okay, so this small dm subtended a small angle d phi at the center. Okay, the half angle then becomes equal to d phi by 2. If I project it upwards, this angle also becomes equal to d phi by 2. Mind you, this d phi is very small. Okay, I've just zoomed out this figure, therefore it looks quite large, but in reality it is going to be very small. Okay, now on this small segment of the chain, I had normal force, okay, acting in the direction which was perpendicular to the surface of the cone. Okay, this normal force had one vertical component. This normal force would also have one horizontal component which will lie on the horizontal plane, right? What is that going to be? It's going to be dn. This angle is theta, right? This angle is theta, right? So it is going to be dn cos of theta, right? That is what I am representing here. dn cos of theta. Okay. This t is going to have two components. One will be in the direction perpendicular to the radius, okay, and one will be in the direction along the radius. Mind you, I'm mentioning this again, this is a very small segment, so don't think that it's a very big segment and I'm writing things down in a very haphazard manner. I've just zoomed things out and I'm writing it. Okay, I'm writing down the equations based on that. So this angle was d phi by 2. This angle will be d phi by 2. Along the horizontal, if you look, the component of t in the horizontal direction cancel each other off. Along the vertical directions, you will see that the components of t, they add up. Okay, so if I look at the first component, it is going to be equal to t sine of d phi by 2. Okay, and this is also d sine of t sine of d phi by 2. Okay, now since this d phi is very small, I can write this down as t d phi by 2, and this can also be written as t times d phi by 2. Okay, and this horizontal component gets cancelled. Okay, basically the horizontal component of t cancel each other off, and the component along the radial direction, they add. Okay, so the total component, I mean the total sum of the components of t along r, they add up and they become equal to t times d phi by 2 plus t times d phi by 2. Okay, there is a component of dn acting in the horizontal direction but in the opposite direction. Okay, radially outwards basically. So I'll put in a minus sign, dn cos theta. Okay, this is the net force acting on this small mass dm radially inwards, and this actually is providing the centripetal force. Okay, what is the centripetal force going to be? It is going to be equal to dm, that is the mass of the small segment of the ring of the chain, times omega square times the radius. Okay, because this small mass dm was also rotating, right, in a circular path of radius r. Okay, so the centripetal force needed for its motion in the circular path is equal to dm times omega square r. Okay, all right. I can simplify this. I can write this as t times d phi. Okay, minus dn. What was dn? dn was nothing else but dm into g divided by sine of phi. Okay, dm into g divided by sine of phi into cos of phi, so that gives me cot of phi is equal to dm times omega square r. Now let's see what dm actually is. dm is nothing else but m divided by 2 pi times the small angle that this small segment subtends on the center, which is nothing else but d phi. Okay, so if I solve for t, I get t into d phi is equal to dm times g. If I take that out as common, I get omega square r divided by g plus cot of theta. Okay, now dm can be replaced by m by 2 pi into d phi times g into omega square r by g plus cot of theta. Okay, d phi and d phi cancel each other off, and I get my t as mg by 2 pi times omega square r by g plus cot of theta. This is what my answer is. So this problem, again, it looks challenging, but it is easy to solve. The concepts are quite simple. You just have to observe the small segment of the chain, write down the force equations properly, note that I have magnified the small segment, so the angle that the small segment is subtending on the center is equal to d phi. So you have to keep a note of all those things. Yeah, the answer is fine. Let me solve the second problem now. Okay, so I have the second problem written in here. Um, in this problem, a car moves uniformly along a horizontal sine curve, which is given as y equal to a sine of x by alpha, where a and alpha are constants. The coefficient of friction between the wheels and the road is equal to k. At what velocity will the car ride without sliding? Okay, so this is the problem. Let me draw the diagram first. Okay, basically I'll draw the curve first. So let's say this is my y-axis and this is my x-axis. A sine curve typically looks like this. Okay, alright, this is pi by 2 and this sine curve has been given to me as a times sine x divided by alpha. Okay, this is what it has been given to me, right? Okay, and on this path my car is moving with a constant velocity. Okay, so this problem is related with curvature of a function or graph. Okay, different points will have different curvature, right? So we'll have to use the curvature formula. Curvature is defined as 1 by r, okay, where r is the radius of curvature. It is defined as f double dash of x divided by 1 plus f dash of x whole square to the power 3 by 2. Okay, this is how curvature is typically defined as. Okay, so in this case my fx is equal to a sine of x by alpha. If you differentiate it once, you'll get f dash x, which is equal to a by alpha cos of x by alpha, and if you differentiate f dash x again with respect to x, you get minus a by alpha square sine of x by alpha. Okay, now the centripetal force that the car will need such that it moves with a constant velocity, a constant speed rather, with a particular radius of curvature, the centripetal force would be nothing else but mv square by r. Okay, now this centripetal force, once it becomes maximum, only then my frictional force is going to be maximum. Okay, so when will this centripetal force be maximum? It will be maximum when my 1 by r reaches the maximum value. Okay, which means that this has to reach the maximum value. Okay, this particular term has to reach the maximum value. Okay, alright, when it has reached the maximum value, it is equal to the frictional force between the road and the tire, right? For a velocity lesser than the velocity which we will find, the frictional force is going to be less, and for a curvature which is lesser than the maximum curvature that we'll find, the frictional force will be lesser than the maximum static frictional force that's possible, right? Okay, so this is going to be equal to k times the normal force, which is equal to mg. Okay, so to make things clear, this is the path on the horizontal surface, right? And the car is moving along this path, so the car is something like this. Okay, it's supposed to be a point object. The car is going to be something like this, and the car is going to move on this path. So imagine this path on the horizontal surface. Okay, don't think that it's moving on. I mean, this path uh, is vertically upwards or something. It's actually horizontal. Okay, so imagine that the car is moving something like this, not something like this. Okay, so m and m gets cancelled. I need to maximize 1 by r in order to get my velocity. So whatever my 1 by r is, I will figure out the value of r accordingly from that. Okay, and I'll substitute that in here and I'll get the answer. Okay, so I've already figured out what f double dash x is and f dash x is. I'll replace that in this equation. I'll get 1 by r is equal to minus a by alpha square. By the way, it has to be modulus, right? Modulus of 1 minus a by alpha square sine of x by alpha modulus divided by 1 plus a by alpha cos of x by alpha this whole square to the power 3 by 2. Okay, now if you observe this, you will see that I want my denominator to be as low as possible and I want my numerator to be as high as possible, and that is possible when this is equal to 1 and when sine of x by alpha is equal to 1, cos of x by alpha will be equal to 0. Okay, if you know the sine and the cos graph, sine x looks like this, cos of x looks something like this. Okay, so when sine x is maximum, which is 1, cos of x is going to be equal to 0. Okay, sorry, so this has to reach its minimum value, which means that 1 by r is nothing else but a by alpha square. I have removed the modulus part. Okay, which gives me r as alpha square by a. So if I put in this value of r in here, I get v as root over k times g alpha square by a. So this gives me the value of v as alpha times kg by a. Okay, so this is what my velocity is going to be equal to. This is the maximum velocity. If my velocity is lower than this value, then my frictional force in that case will never be equal to k times mg. It is going to be less than that, because in case of maximum curvature also, the minimum centripetal force required would be the centripetal force required in that case would be less than k times mg only. So yeah, these were the two problems. If you have any doubts, please comment. Okay, I'll try to rectify that, and I would also request you all to like the video and subscribe to my channel if possible. Okay, all right, bye. We'll come up with new problems and solutions in the next class. All right, bye.